Join us as we explore logistic regression, a fundamental algorithm for classification problems in machine learning. Logistic regression is a classification algorithm that predicts the probability of a binary outcome, like yes or no. First, let's understand what classification means in machine learning. Classification is the task of assigning data points to discrete categories, unlike regression, which predicts continuous values. Binary classification involves two possible outcomes, like spam or not spam, disease or healthy. Here we see two distinct classes of data points. Our goal is to find a boundary that separates them. You might wonder why we can't just use linear regression for classification. Linear regression predicts continuous values that can be any number, not bounded probabilities between 0 and 1. Linear regression can produce values less than 0 or greater than 1, which don't make sense as probabilities. Logistic regression uses the sigmoid function to solve this problem. The sigmoid function is defined as 1 over 1 plus e to the negative z. The sigmoid function maps any input value to an output between 0 and 1, perfect for probabilities. The sigmoid curve smoothly transitions from 0 to 1 with the threshold at 0.5 for classification. Now let's see how logistic regression combines linear equations with the sigmoid function. First, we compute a linear combination, z equals w1 x1 plus w2 x2, and so on, plus bias b. Then we apply the sigmoid function to get the probability that y equals 1 given input x. The model takes input features, computes a weighted sum, then applies the sigmoid to output a probability. Logistic regression uses log loss, also called binary cross entropy, as its cost function. The log loss function measures how far our predictions are from the actual labels. Log loss penalizes confident wrong predictions heavily, encouraging the model to be accurate and calibrated. We optimize this loss function using gradient descent to find the best weights. The decision boundary is where the model separates the two classes. When the predicted probability equals 0.5, we're exactly at the decision boundary. The decision boundary is a line that separates the two classes in the feature space. Once trained, we use the model to make predictions on new data. If the predicted probability is greater than 0.5, we classify the example as class 1. If the probability is less than 0.5, we classify it as class 0. Mathematically, y hat equals 1 if the probability is at least 0.5, otherwise it equals 0. Logistic regression has numerous practical applications in the real world. In medicine, it can predict whether a disease is present or absent based on symptoms and test results. Email systems use it to classify messages as spam or legitimate. Banks use logistic regression to approve or reject loan applications based on credit history. Companies predict whether customers will leave or stay to target retention efforts. Let's summarize the key concepts of logistic regression. Logistic regression is designed specifically for binary classification problems. It uses the sigmoid function to ensure outputs are valid probabilities between 0 and 1. The model is trained by minimizing log loss using gradient descent optimization. It creates a decision boundary that separates the two classes in the feature space. Despite being simple, logistic regression is widely used because it's fast, interpretable, and effective for many classification tasks.